So thanks for having me, also to the organizers. I'll be talking about our most recent project today, which includes two parts. One is what we call an application-oriented way to benchmark digital quantum simulation, and then also a part on combinatorial optimization on digital hardware. For the sake of time, I'll only be talking about the benchmarking part today, but you can find all of the details in this archive preprint. So this work was done together with Guillermo Mazzola from the University of Zurich, who is also the PI for this project, as well as Daniel Egger and Ivano Tavernelli from the IBM Quantum team in Zurich. So I will quickly motivate why we thought we need yet another way of benchmarking, then discuss briefly the Kibbe-Zurich mechanism, as it is what we will benchmark against in this work, and then show you our results. So standard ways of benchmarking quantum computers are usually very local, so they give you individual error rates for basis gates or coherence times for individual qubits. Or there also exist more global benchmarking schemes that aim to supply some kind of error metric for the entire chip or qubit subsets of that, but usually involve quite a heavy degree of randomization to make the benchmark somewhat agnostic of device specifics, such as connectivity of the device or basis gate set. I would argue that, or all of these are very important and relevant, but I would argue there's a bit of a discrepancy between error rates reported by these benchmarks and what we're able to run on current day hardware. And what I mean by this is if you were to take these error rates and try and estimate what kind of error would you expect running some application circuit you might be interested in, the error would probably be really bad that you get from this estimate. But in practice, we've seen this week and in the last couple of years that we're able to run pretty large circuits with thousands of 2-qubit gates, in one case even above 10,000, over 100 qubits, and get at least qualitatively good results. So what we thought would be nice to have is some way to predict how many or how deep of a circuit can I expect to run before noise becomes detrimental. And this discrepancy that I mentioned, I think, is mostly due to two reasons. First, obviously, because we have very sophisticated error mitigation techniques by now. Second, the circuits that we're currently running are extremely structured. So they are made up of repeated layers, and even within each layer, the structure of 2-qubit gates is very ordered, and so you're susceptible only to part of the noise that you would encounter in a completely random circuit. So the proposal that I'll quickly flash here and that I hope will become more clear in the remainder of this talk is that we use universal scaling laws to benchmark against, in the sense that if we have some observable that we can measure as a function of evolution time, and we know from theoretical predictions that this observable should adhere to some universal scaling law, then we can say if we reproduce this scaling for n time steps, and each time step corresponds to one circuit layer, then we can coherently simulate n circuit layers. And this would be a nice way to predict how many circuit layers can I expect to run reliably in applications such as Hamiltonian simulation, QAOA, so optimization problems, variational methods, and so on. So if you take one thing away from this talk, I want it to be that we propose to benchmark against universal scaling laws. Now, there exist different ones that you could choose to benchmark against. What we propose in this work is to benchmark against the Kibbe-Zurich scaling, so the scaling predicted by the Kibbe-Zurich mechanism. And we do this because it is applicable, or applicable in a regime of simulation time and qubits counts that is attainable with current day hardware, but of course it's not the only scaling you could envision and benchmark against. So if anyone comes up with a more suitable scaling, then I'm happy to hear about this. So I will quickly introduce this Kibbe-Zurich mechanism. It shows up in quantum annealing, and quantum annealing is essentially this method where you have this kind of Hamiltonian, I think the pointer, so you have this transverse field Ising model with two time-dependent coefficients, and these time-dependent coefficients are what we call annealing schedules A and B, and essentially you prepare your initial state of your time evolution in the ground state of the term on the left, And then during the time evolution, change the Hamiltonian from the term on the left to the term on the right by ramping down, respectively ramping up these two coefficients A and B. And so if you do this slow enough, then the theory is that you end up in the ground state of the term on the right. Okay, in this very simple case of uniform couplings, the ground state of the term on the right is known, and it's a simple ferromagnet. But even in this case, there's a bit of an issue, namely that we run into a critical point during these dynamics, which means that approaching this point, the relaxation time of our system becomes very large, diverges, and so the system can no longer relax to its instantaneous ground state at some point, which will inevitably lead to leakage into higher excited states, and as a result, defects in our final state. Now, in this uniform coupling case, a nice metric for the quality of the solution is the density of defects, and we will measure it with this observable in our experiments. And now the Kibble-Zurich mechanism describes this defect production and quantifies the density of defects as a function of the total evolution time, as a function of the annealing time. And it predicts this universal power law decay that's only dependent on the dimension of the system, d, and the two critical exponents, z and u. So in the 1D case, this comes down to a t to the -1/2 scaling, and this is what we want to benchmark against. So now we saw yesterday in Emmanuel's very nice talk that if it comes to phases of matter or spin systems, there's hardly anything that analog simulators haven't done yet. And so also here, we're of course not claiming that we're the first ones to implement this kind of dynamics on a quantum device and observe this mechanism. In fact, this has been done many times on mostly analog simulators. And you can also see this in this quite nice figure here that I took from a D-Wave paper from a couple of years ago, where you can see this mechanism in action. So you see that for longer annealing times, you end up with less defects in your spin chain on this top right plot. And the density of defects that you see here in this plot, plotted against the total time of annealing, follows this predicted scaling by the Kibble-Zurich mechanism. So this green line very nicely until it deviates at some point due to noise in the device. And then in these analog devices, noise, depending on the system parameters, will lead to this deviation, but then maybe a further increase, which is very different from what we will see in the next couple of slides. So the crucial difference is that we do this digitized, so we don't do analog simulation, but we implement this time evolution in a digital way. So we use a very simple Trotter formula of order 1 to discretize the time evolution operator, and then end up with this very structured layered circuit that I showed you in the beginning, where now each time step or each additional time step means we prolong the evolution time. So each layer is decomposed into many, many gates here, and I'm just flashing this example of one of the experiments that we did to show you that what's conceptually different about an analog simulation is the kind of noise that we encounter and the effect that the noise has on our results. Namely, every qubit, of course, is noisy, but also every gate is noisy, and so this noise accumulates throughout the simulation. So I will discuss this effect that the noise has on the simulation outcome in a few slides. So now I hope that this schematic became a bit more clear. So what we propose to do is benchmark against such a universal scaling law, and as you can nicely see in the schematic figure here on the bottom right, so these are not actual results, this is really just a schematic. If we know that each point here is an additional time step, and we know we can reproduce the scaling for n time steps, then we can conclude that we stayed coherent for n circuit layers. But beyond this number of circuit layers, our simulation is not to be trusted anymore because there's probably too much noise in the circuit. Okay, so this is the general idea. So now I mentioned that I will discuss the effect of noise on these results a little bit. So we did some state vector simulations before going to experiments, and here I just show you the Kibble-Zurich, the density of defect scaling as a function of the total evolution time obtained from state vector simulations for a very small system, 12 spins periodically arranged. Now this number 12 is important because finite size effects in this are pretty large. So finite size effects result in these bumps in the curve and this drop-off pretty early on. You will not see this in larger systems, and you will see this drop-off much, much later. So this will not be relevant for the results I'll show you later. But we wanted to study the effect of noise, like I said, and so we took the noise from one of our devices, from IBM Sherbrooke, and simulated this noise. And so what's nice, if we do the state vector simulation with simulated noise on top, is that we can scale this noise. So we can simulate 10 times the amount of noise that we would see in the hardware. We can simulate 1% of the noise. And so this is indicated by these factors eta here. So these are the scaling factors of the noise model, basically. And so what we also could intuitively expect, namely that for lower noise, we can reproduce the state vector, the noise-free results for longer evolution times, is also what we see here. So these lower curves here are basically lowest noise, and the upper curves are the largest noise. But we see that the lower the noise, the longer we can reproduce this scaling, and we get this deviation at later times. And then we see the characteristic of this noise, namely that we end up with a bit of, or a minimum in the density of the effects a bit after this deviation, and then an increase. So contrary to the analog results I showed you before, we don't get this decrease of the density of the effects again, but we get simply increasing density of the effects. So we also did this, or simulated this exact system on the device, and we see that the hardware results actually match the simulated noise at a scaling factor of 1, so at the plain noise level pretty well. So this is quite nice, and gives us confidence that we can indeed say if we deviate from this expected behavior, we can conclude that at that point the simulation decoheres. So we first simulated this in a 100-qubit chain, so an Ising chain of 100 qubits that we mapped to two of our devices, IBM Torino and IBM Sherbrooke, and then carried out this time evolution and measured this density of defects as a function of different total evolution times. So this is what you see here plotted, so density of defects on the y-axis and the total evolution time on the x-axis. So every point is a new simulation, basically, with a longer evolution time. But every point also is, or every additional point is one extra time step, okay? So we did this for different error mitigation and suppression techniques, but very simple ones that you could basically use out of the box. And what we see here is quite nicely is that we obtain this expected behavior of a decay of the density of defects according to this expected scaling, then a deviation, and followed by a minimum in the density of defects, and then this increase that we expect from noisy simulations. So this is a good benchmark, I would argue, because with large simulations, we retrieve what we expect from simulations, from noisy simulations, and in part also from theory. So of course, with the progress of hardware here, we would expect that this trend follows the expected scaling for longer. So just quickly from this, we could then conclude that on the left, we reproduce roughly 5 trotter layers before noise kicks in, or it becomes too detrimental. On the right, roughly 7 trotter layers for the best curve, which corresponds to roughly 1,400 2-qubit gates at a depth of 28, 2-qubit gate depth of 28. So we wanted to do this on the heavy hex lattice as well, so which is the connectivity of our IBM devices, because it's, or it might be a bit closer to application. But I showed you before only the scaling for the 1D case. And for the heavy hex lattice, we don't know the critical exponents and hence also don't know the scaling. So this is to be taken with a bit of a grain of salt, because we don't have strong theoretical underpinning for these scalings. But we nevertheless wanted to see what we get. And so first we did some state vector simulations comparing 1D to the heavy hex scaling to true 2D, so to the square lattice. And already with this, we see that in this regime of applicability of the Kibble-Zurich mechanism, which is roughly here, we see that the heavy hex coincides with the 1D curve, at least qualitatively. And then this drop-off happens a bit sooner, but the Kibble-Zurich regime obeys the same scaling, whereas in the 2D case, we get a different scaling throughout the entire curve. This is intuitively also understood when we look at the degree of connectivity, let's say, where we see that the heavy hex is actually much closer to 1D than it is to 2D. So to use this 1D scaling as a guide for the eye in these density of defect scalings on the heavy hex, I think is quite warranted. So now, mapping this dynamics to the heavy hex, we get slightly deeper circuits. So for each layer, we now have a 2-qubit gate depth of that is 50% larger than in the 1D case. And so we did these same experiments, and again reproduce what we expect from our noisy simulations. So we get this deviation with this expected scaling, then a decline with this expected scaling, then a deviation at some point, followed by a minimum and the increase again that we saw in noisy simulations. And so also here, we could conclude that we could simulate roughly 3 Trotter layers on the left, so on IBM Torino, using the whole chip, so 133 qubits, and roughly 5 Trotter layers on the right on IBM Sherbrooke, which again corresponds to 2-qubit gate depths of 30 and a gate count of 1400 of only 2-qubit gates. So yeah, this is what I wanted to show you in terms of results. And so concluding, I think the most important part is that we propose benchmarking against theoretically well understood and well-known scaling laws. And the Kibble-Zurich mechanism is one of them, but already in this model there exist different scalings that are theoretically known and understood. So there could be other ways of comparing to different scaling laws. This doesn't require any classical verification, and these scaling laws are defined in thermodynamic limits. So it's really very easily scalable to larger system sizes. They could be used for qubit selection by taking partial or qubit subsets on the device and measuring the density of defects there. And they're very transferable to other applications, since Hamiltonian simulation in itself is a subroutine of many different applications. But these kinds of circuits are found not only in Hamiltonian simulations, but in optimization, so quantum annealing or QAOA, in variational methods for spin systems, or certain quantum machine learning kernels. So with this, I'll be open for questions. Thank you. Questions?
One question, so you raised the question of what kind of universality you expect for the heavy hex, right? But would it not be reasonable to expect that maybe early times it looks like a 1D system, and at later times you'll have a crossover, once its time of evolution is long enough to notice the roots, and then you would expect 2D critical exponents, perhaps?
Yeah, that's a good point. I haven't looked into this, but yeah, that's something to consider if we want to make this more theoretically sound. Yeah. Thanks. Yes. Oh, or sorry, you do it. Oh.
So in your, so you're relying on the universal properties of this phase transition.
Mm-hmm.
And I was just curious, do you know if you're getting the non-universal parts correct too? Like maybe somehow universal parts might be more robust and survive better.
Yeah, that's true. So this is something that I've seen in the analog literature too. So we did look at non-universal, distributions of the defects, and we do get qualitatively the expected behavior there.
Okay.
So in analog simulations, this is something they need to verify, because their machine could reduce to a thermal annealer, for instance, and reproduce this universal scaling also by classical means. Here, I would argue it's less of an issue because we solve a Schrödinger equation, and it's, if we reproduce the noise-free results, so to say, then I think it's quite intuitive that it should be, purely quantum, the evolution. But nonetheless, we did check these also, and I can show you. It's in the appendix also.
I'm just curious. Yeah, thanks.
Thank you.
Let's thank Alex.